Let's now look at part 5, half-wave rectification of an alternating current. Okay, so to teach you this, I must first introduce to you or remind you what a diode is. A diode only allows current to flow in the direction of the diode. So in this case, a play button, right? So it's a circuit symbol, and the current will flow in the direction of the play button. Okay, if you look at the device itself, it looks like this. This silver band denotes this straight line part of the diode. Okay. The IV characteristic of a diode, this is also again a reminder, right? I didn't put it in my notes because it's something just to remind you. There is a breakdown voltage, right? So in this left hand side, it is a reverse bias and there's a breakdown voltage. And in the forward side, past a very small voltage, right? The current increases very quickly for a very small change in V. So practically the resistance is close to zero because you can reach a very high current for a very small voltage. Okay, so that's something to remind you about. Now let's talk about how it works, right? If you place a diode in an alternating circuit, right, alternating current or alternating voltage, uh, here we have what it looks like in a forward bias, right? We're introducing also to you the terms forward bias. In a forward bias, the diode is in the correct direction. The current flows through the diode, right? So that's not an issue. In the reverse bias, notice that the battery wants to send the current. There is no current flows yet. Wants to send the current through the circuit, but it's blocked by the diode. It's in the reverse direction. It's in the wrong direction, right? So in the reverse bias, and then therefore no current flows. Okay. Hence, if you then connect a alternating voltage with a diode and a resistor, right? What happens? You'll see that whenever the voltage is positive, the diode conducts the current. So if you put an ammeter here, you'll measure a current, right? In the opposite direction, that means in the second half of the period, the voltage is now positive on the right hand side of the terminals. It tries to go down this way, but it is blocked by the diode because the diode is fixed in direction. It blocks by the diode and you get nothing, right? No voltage, sorry, no current flowing through, right? There is an alternating voltage. The voltage is still there, but you have no current flowing through. So essentially, right, if you just have the resistor without the diode, you will have alternating voltage and you should have got an alternating current. With a diode, you have now a DC. Why? Because the current didn't go negative. If it didn't go negative, even though it went zero, it did not change direction. It is hence what you call a single direction, and it's hence what you call a DC. Right? So you have converted effectively an alternating current or alternating voltage to a DC current. Okay. So this process of converting AC to DC is called rectification, right? And the diode is said to rectify the AC. Okay, let's now talk about work example 6, right? You have here a alternating current described by I equals to I naught sine omega t, and it's allowed to flow through a resistor, and then a diode is connected in series. Okay, so the current can only flow through in one direction. The graph of the current is then given as shown. Okay, so we are now combining what we have just learned using of a rectification using a diode and what we have learned in part 4 in the previous lecture. Right, we're trying to find the root mean square current here and the average power dissipated over time. So first, right, oh yeah, so in a standard question, the graph will not be given, right? So in a A-level question, you're supposed to draw this graph yourself, right, and work it out from there. So here, using the graph, right, so if you take the square of the graph, you should get this. That means you get half, right? Every time the current is present, you get the I-square graph here. When the current is blocked by the diode, you get a flat line. Right? Remember in the previous chapter, the I-square curve grows like this, right, throughout. Now half of the peaks are missing. Okay, so you have done the square now. What must you do? Well, you need to take the mean, right? And you learned, right, remember in the previous part, that from t to t2, the mean value is half of the peak value, right? The peak value is I0 square, right? That's what we have learned, and we agreed on mathematically that that is in fact the average value. But from the next half of the value, right, the average value is actually 0 because there's nothing there. So if you want to take a true mean across a whole period, so half the time is at I0 square over 2, half the time is at 0. If you want to take the real mean throughout the whole period, right, you need to do the following, right? You need to first take I0 square over 2 plus 0 divided by 2. Right? Imagine I give you 2 apples a day and 0 apples the next day. And I repeat that every 2 days. The average number of apples you get is actually 1. Alright? So here you have 2, you have 0, you get 1. Right? That's what it means over here. Okay, so here this question is then quite interesting, right? Because you are applying the first knowledge of how to mean a sine square wave, right? The mean is half of the peak value. Then you must also have the mental awareness that half of the time the sine square wave is missing, so the average of that is a further half of that value. Okay, so now we have established that the mean value, the mean square value, is I0 square over 4. Okay, so what's left is to take the root of that value, right? So the root of the mean square value is I0 over 2, right? You square root I0 square over 4, you get I0 over 2. Okay, so you root it back, you get that. You find that the root mean square value of a half wave rectified sinusoidal wave is I0 over 2. Okay, so graphically what it means is take the graph, you square it, take the mean, you square root it, you get back this value. Okay, yep. If you want to find the average power, now it's easy, right? It's just the root mean square value squared times r, right? Since we know that the root mean square value is I0 over 2, if you square it, you get I0 square over 4, so which is this, right? Times r. If you recombine, you get it as I0 square r, which is the max power P0 over 4, right? So what it means is that in the rectified circuit, right, the average power you get is a quarter of the peak power. So take some time to think about it, right? How does this compare to the non-rectified circuit? Remember, in the non-rectified, that means the sinusoidal current, the power, if you flip back a few pages, is given as P0 over 2. This value here, when it's rectified, is P0 over 4. Do you realize that it's halved? Right? And it shouldn't come as a surprise because the diode blocks out the current half the time. So essentially, this is a natural logical conclusion. Okay? Right. So with this, we can finally do the review on the summary of equations, right? I found this to be very useful. I think before I lectured this, right? The notes only had the first two, whereas in the questions that they like to set, this part comes up quite often. So I thought it's good to generalize this and have you remember it. Then of course that comes the second part, right? Can I then just apply the equations like that? I would suggest yes, if it's an MCQ, but in the structured questions, maybe you should look at the marks and decide whether it requires you to prove these equations or not. Okay, so meaning play by ear, make your own judgment. There's no one solution that fits every case. Right, with that, I've come to the end of part 5.